Welcome to Krishna's classroom. I am Krishna Kumar. We continue from where we left yesterday. And before I go to introduce the real number system, we've already done positive rationals, what we call Q plus. Now, what we want to do is to introduce R plus, the so-called positive real numbers. But before that, I want to make some remarks on what I said yesterday. Now you recall the particular identification of rationals as the fractions have been identified as the lattice points. That the fractions have been identified as the lattice points here. That is the points in the first quadrant of R2 with what are called integer coordinates. Now a general point in this is given by m n, which corresponds to what is called m by n as a fraction, and this belongs to what called n cross. Okay. Now there is no question of n becoming 0 here because 0 is still not there. Okay, fine. Then I said that in the class of fractions we introduce a what you call an equivalence relation. And through the equivalence relation, we build some equivalence classes. And these equivalence classes constitute what is called the Q plus. Okay? So we get a large number of new objects. And a typical, and this m by n, suppose this is m and this is n, then this is the point m, n, and you join this to the origin, and then you get a line. Now you consider all the lattice points lying on this line. There are several because mn is there. Then you see that Km, Kn is also there for every K. So they all lie on that line. So this particular line or the lattice points lying on this line is identified with the rational number m by n. Okay. Now let us see what more we could look at. So if you consider this angle as theta, then you have cot theta is equal to m by n. Therefore, you see that all these cot theta with the or All these lines for which cot theta is equal to some m by n is given by. So you have got a lot of radial lines which are equivalent, and then you see that they fill the space. Apparently they fill the space, but not quite. Okay. So each line corresponds to a particular rational number. The only condition is that the particular line should pass through one of these lattice points. Okay, of the form n by. The question is, does this fill the whole of, say, R2? Unfortunately, it doesn't. There are gaps. So this is one of the things that you have to look at. So it is cot theta, where theta is such that this is equal to m by n. So you have theta given by and cot theta given by m by n. Now this collection of cot theta takes care of all rational numbers where cot theta is given by. So this is the end. So each line corresponds to this. The only condition is that the line should be passing through a point with the coordinates given by the lattice points. That's one remark. The second remark I want to make is a result that is there for all these rationals. Now you see, given plus, you've already got q plus, there exists such that y is less than n times x. This property is what you call, this is called the Archimedean property. Simply says the following. Now you recall our positioning of the rational numbers. So you have 1 here, 2 here, etc. Then this 0 is not included. So it's a half length that we have picked up. Now you see that the q plus, the elements of q plus, x belonging to q plus x is some point here. Anywhere, it could be anywhere. So if, see, I will try it again. 1, 2, n. What it says is the following. Now if x and y are 2 points, say x is this and y is something this, or maybe you take mark y somewhere here. Then what it says is that if you walk through with the length of a step given by x units, then through n steps you can cover this. So you have an n such that this is equal to n times. It's not necessarily the same n, it is some other n. Okay, so there exists a positive integer or a natural number n such that y is less than n times x. So you can move from here x, 2x, 3x and so on. You can come to nx. So there is some n with the property that y will be less than nx. So there are several n's of this property. Okay, but certainly you can cover this through n steps of each step length of x units. Now this is the argument property, which is a very important property which we use in many of the proofs, proving many of the statements that we make. Now yet another result that you can prove is the following. It is given y belonging to q plus, there exists n such that n is less than or equal to y less than. What it says is that there exists a natural number n with the property that y is squeezed between n and n plus 1. Now y also could be a natural number, then of course it is going to be equal to the particular natural number n. Even otherwise, it is squeezed between n and what is n plus 1? N plus 1 is the successor of n. So it falls between n and its successor. Now this is a very important result which we will be using in many places. Okay, so these are some of the properties of the rationals, positive rationals that we have constructed. And you see, if you just take natural numbers, there is no such thing. Either it is equal to n or n plus 1. It is there, really there, but certainly, the y is going to be either n for some natural number. Okay. So this is an important problem. So with these remarks, we need a proof for all this. I am not going to give the proofs. Then of course, it was shown that, this doesn't cover all the points on this. Okay, that is, q plus is not, there exists. For instance, you take this one. Take the equation equal to. You ask the question, does there exist? Now the answer to this question is that there does not exist x belonging to q plus such that x squared equal to 2. In fact, there are many numbers like this. Okay. So, this particular equation, this is not a linear equation. Because if you were to take q plus, see, if a and b are given, Ax equal to B for A belonging to Q plus, B belonging to Q plus always has a solution. Okay, and this is given by X is given by B by A, the class B by, which is which can be identified as a rational number, because B is a rational number, A is a rational number, therefore this is a rational. So it's a fraction and you get this. Okay. Now this is a linear equation, whereas this one is a quadratic. So the quadratic equation x squared equal to 2 with, if you search for the solution of this in Q plus, you do not have a solution. Okay. So in fact there are so many points on this which are not accounted for as an element of Q plus. And therefore what we do is we go for further extension. Okay? Right? But this equation always has a solution. So as I said earlier, and because this equation has a solution, so it follows that Q plus multiplicative group, which is also commutative, by which I mean that Q plus is closed with respect to multiplication, or multiplication is what you call a binary operation on Q plus, which means if x belongs to Q plus, y belongs to Q plus, x times y is again in Q plus. That is the meaning of that. Then you have, it is associative. Multiplication is associative. Associative in the sense that x, y, z equal to x, y, z for every x, y and z belonging to Q plus. The third property is x into y equal to y into x. That is, it is commutative. And the fourth property is that given x, and this is y is unique and y is defined as x inverse. So every element in Q plus has a multiplicative inverse. And of course, before that, of course, 1 belongs to Q plus, and 1 has the property that x into 1 equal to x or X. That is the existence of the identity element. Then this is the existence of the inverse. So it's a commutative tool because of these properties. It's called a commutative. But it is not a group with respect to addition. Okay. Only the associativity is satisfied with respect to addition. Commutativity is satisfied with respect to addition. And of course, it's a binary operation. Addition is a binary operation on Q plus. But it does not have an identity element. There does not exist any y such that x plus y equal to x in Q plus. So also there is no inverse. I mean, therefore it falls short of becoming a. Now we want to rectify these deficiencies. I mean, that is one thing. And if you look at on this line, then the problem is, again, there are a lot of gaps, and we have seen that if you consider the equation x square equal to 2, it doesn't have a solution. Okay, and this, this is one of the early things that you learn to prove that square root of 2 is not. You have a very well-known proof of using reduction, that is assuming root 2 equal to 2 by 2. Then you can know common factor between p and q. Then you get 2 equal to p square by q square. So p square equal to 2q square. Therefore, p square is even. Okay, that's what you infer, and from that you arrive at the condition that there is a common factor between p and q given by q2. Okay, so p square is even, which says p is even. P is even means it is equal to twice p prime, and therefore what you have, p square is equal to 4 times p square. So this will also give 2 square is even, which means q is even. Therefore between p and q there is a common factor 2. So that contradicts our basic assumption. So that's how the proof goes, and you can have a look at this. It's the first time probably you come across what is called using reduction. Okay. Right. So there does not exist, root 2 is not rational. So we have to, capture these kind of things. How do you do that? One of the ways, these days I think seldom Dedekind cuts are taught in a classroom. Simply say that there exists a completion of this. There are very many ways of doing it. But let us go through this idea because it's very fascinating. So you have now this set. And this is full of gaps. Like root 2 is not accounted, e is not accounted, pi is not accounted. You can look at it's difficult, it's not easy to prove that pi is rational or pi is not rational, e is not rational. All these are not very easy to prove, but what it brings out is that there are plenty of points on this half line which do not correspond to any rational number. Okay? So how do you capture them also into our code?